Okay, let us begin. Today we're doing baby Ehab partitions again. This was from a while ago, but the idea is you're given an array of numbers and trying to make it so that there's no way to divide the array into two groups in which the sum of the elements is not equal to each other. So I did some practice earlier. For example, let's see, 1, 2, 3, 4, 5, 7. So there is a way to divide these into two groups. You can do 4, 7, and the rest. So this would be 11, this would be 3, 6, 11. So yeah, there is a way. So that means in this problem, you actually don't want this to happen. And you're trying to, in order to do that, you want to remove elements so that it's impossible to make it so that you can divide by 2. So you can probably remove, I don't know, 1 and you'll be fine. Like, and yeah, that's the goal of the problem. So yeah, I'll start giving the solution. So first things first, how did I figure out so fast that it was impossible? Well, if the sum is not divisible by 2, it's impossible. So if I took it that 1, 5 plus 16, 21, there's no way to divide 21 equally into 2 parts. So we know that's impossible. Second, you have to use knapsack DP. Well, if you don't know what that is, it's knapsack dynamic programming. You should probably search it up. But here's the deal. So you can technically brute force it and get to the end and try to figure out every single possibility, but that's too slow. It goes to 100, which doesn't seem like much, but it's like 10 to the 30th if you do 2 to the 100. So it's impossible. It's impossible. However, with knapsack DP, you can get it into n squared time. Right? I think, yeah, because n by n. So what I did, I learned this today actually. I use bit sets. It's pretty cool. It's a nice way of doing basically the exact same thing as DP, except for bits. There's nothing really to do with zeros and ones. It's more the ability to shift bits. This may look like Arabic to you, but it's not too bad. So I'll quickly explain it. So let's see. Okay, so we'll go with this example. 6, 3, 9, 12. So, okay. So we start off with 1 right here. Start off with 1. So the first element will be 1. And then we add and shift to the left by the amount here. So shift 6, right? That would be like 1, 2, 3, 4, 5, and then 6. At the end, it copies it. It's because it's an or equals. So it will always have this 1 at the beginning. Always, 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 always. And then you'll keep on doing it, shifting every single one, adding zeros to the end. I think, yeah. And you'll keep on doing it, just adding zeros. I think I'm doing this wrong, but you get the point. You know what? Screw it. I'm not gonna do it. But eventually, I'll output it. I'll make it so that it outputs. Make sure it's not lagging. It is lagging a little bit. Okay, well, that sucks. But I don't know why it's not. Okay. Ah, shoot. Wait. Okay. Not that. Don't worry about that. Don't let that scare you. It's just because of the size. So it actually looks really nice. And at the very end, you check if it's available. So each of these ones represents a possibility of landing on that number. So this would be 1. There's no possibility of having 1. or actually wait, I think this is supposed to be 0. Yeah, this is 0, this is 3, this is 6, this is 9, this is 12, and those are all different possibilities. This would be 3 plus 12, so 15, and each one represents like, yeah, it is possible to get to that number. Now the easy way is it possible to get to the sum divided by 2? Sum's up here, and if it is, well, that means the other group has to be equal to divide by 12. And yeah, that's just basically knapsack in like really easy form. Actually, I think this is O of n squared. Wait, I think maybe, or not n squared. I think it's just O of n. I think knapsack is O of n. No, knapsack is O. I'm like tripping myself up. Knapsack. I don't know. Knapsack is O of n times m, right? I'm 100% sure. I'm tripping myself up. Wait. Knapsack, blah 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 blah. O of n times w. And then here, is there any faster way? No. It just has lower time or space complexity. Anyways, yeah, I'm tripping myself up. What am I doing? Okay, but you'll get the point. And 32, or this middle number, represents the highest possible like value that the sum of the array can have. So that would be 100 times 2000. And so you have about 1, 2, 3, 4, and then 5. 5 is just the extra number, so it doesn't like space out from extra numbers. You usually add 5 to like an array or something like that for sizes, just in case, so you don't get an out of bounds error. But yeah. Now let's get to the actual. So now, okay, with this, we've now proven that it is possible to get a group. And so the idea is, if it is possible, you do this. If it isn't, you just put 0, which is here. It's impossible, and you don't have to do anything. You already solved it. Now, at first, it may seem daunting. Like, there's a lot, but as you can see, it's only like 4 lines of code. And the idea is, okay, well, first things first, I don't know if there's bit set in Java. They're probably, I don't know. I'm just not a Java person. But here, the idea is you, oh, okay, let's get out some more ideas. So maybe like something like this, or yeah, maybe something like this. 1, 2, 3, 5. Yeah, this should be 4, 9, 16, 27. We'll have another 1. Actually, we'll have another odd one. 9, 11. Okay, this should be divisible. Now, so what do? Well, technically, this is a little bit of a trick question. You only really need to remove one number, and if you only need to remove one number so that you can, yeah, you only really need to remove one number. And in a sense that, because, okay, so if I just remove 1, now the whole thing's odd, because there's 3 odd numbers plus 2 odd numbers, and we already know that if there's an odd number of odd numbers, it sounds a little weird. That means it's odd, and where you only need to remove 1. This stuff right here is, you want to get the lowest possible bit, right? So let's say there's no odd numbers, or, well, if there is no odd numbers, it's always, right, yeah. Okay, so yeah, if there's multiple odd, or if it's all odd numbers, you just remove one odd number and you're fine. Any one of these, you're fine. Now, if it's all evens, 2, 4, 6, 8, 12, and you're trying to make it unable to partition, all you have to do is divide the whole thing by 2, like for every single number, until one of them turns odd. So 1, 2, 3, 4, 6, and you can just partition any number any odd number and you're fine. Now, why does this work? Well, buddy. Because if you have, technically they're equivalent. They are equivalent in a sense, because 4 plus 6, or what am I doing? If you add the whole thing together, I don't know how to make this bigger. If you add all of it together, 3, 6, 10, 16, all you have to do is make 8 and you're fine. So 1, 3, 4, 2, 6. And you'll notice this is the same idea, the same indexes. This goes with this, and these go together. Oh wait, this. The 12 goes with that. I messed up. Okay, so 12, 6, and 7, and 1, or I mean 2. 2, 6, and 12 is the same indexes as 6, 3, and 1. Or wait, not. I tripped up. Okay, my bad, guys. I'm so bad at programming. What am I doing? Okay, let's try this again. 2, 4, 6, 8, 12. 1, 2, 3, 4, 6. Okay, well, if we add all these together, 6, 12, 20, 32, we need to make 6. So we only need these two numbers and then the rest. Same idea here. If you just divide every single number by 2, if they're all even, remember, if they're all even. If you divide every single number by 2, right, you'll get the same number. And this also needs 8 because the total is 16, as I said before. So you need the same indexes, and it's the same idea. So nothing changes. Okay, the groups don't change. That's what I mean. The groups don't change. Now, if you just remove the odd element or the lowest odd element, it's different. Now this is 7 and the rest is 8. If you remove that, 10, 18, 30, or this is 14 and this is 16. Voila. And also, you can't really, you can't make 15 out of this either. So that is the idea. I don't know exactly the proof, but it was a very interesting solution. The cool thing about this is when I connect it to bits, and if you notice my code, you'll notice that it has built-in counts, or count 0, count z. There's also count ones, or I forgot the other one. I think it's like count p. I'll need to search up the Arito. Arito log. This guy's a really good, smart dude. I think he's one of the #1 in the world. But there's like a bunch of these built-in functions in C++ for these things, and so he makes this blog because so it makes this blog and it's really useful. And I can't find it. Well, that sucks. But basically, built-in count zeros. It counts the amount of zeros within a given number. So parentheses, vi, which, okay, so let's just run through. And so cn is just input, so c input, that's what it means. Inputs n gives a vector or an array list in Java of size n. You also input that, then you check. This checks if it's possible to divide it from earlier with bits, and then if it is not, or wait, yeah, okay. If it is, wait, I think this returns this if it's true. Wait, did I just, okay. Wait, position, this should be true, or this should be false. This should be false. Sorry. Okay, yeah, okay. So if it returns true, which means it is unable to be solved, you go here, or I mean, if it returns true and it is grouped into divisible by 2, you do this, and if it isn't, you go to 0 because you don't need to change anything. You're trying to make it not able to partition. That always tricks you. So, okay, back to this. So this 12, this is basically 2 to the 12th is greater than 2000 because that's like 2048. You don't need to check it. Yeah, you don't need to check. That's the highest number. I think the tutorial put 12 or 20. But 12 is actually the minimum number. You don't really need to go over it. So then you count the amount of zeros, because the neat thing about it is you really only need to find the guy with the lowest amount, or the lowest one, or the lowest insignificant bit in more mathematical terms. So let's go back to the 1 or the 2468 solution, or 2468 10. I don't know why I did 12. I skipped that for some reason. 6, 12, 20, 30, 15. Oh, this is impossible actually. Wow. We'll go back to 12 then. And since this is possible, we'll divide everything by 2, as I said earlier, because it gives us odd numbers. And we'll go for the least significant. Yeah. And so 1 would be 1, 2 would be 1, 0, this would be 1, 1, 1, 0, 0, 1, 1, 0. And you'll notice that this guy has the lowest 1 because there's no zeros trailing after it. And also 3 works too. Yeah, so minimum, and basically you are given, wait, 1, 2. Yeah, so, yeah. So it just gives you the lowest 1. So this would be the lowest least significant bit. And so yeah, that'll be it. I'll submit it. I think it should work. C dot baby Ehab. I don't know what Ehab is, but actually press enter. And it should give me accepted. Accepted. Yeah. So that's it. Oh yeah, the reason why it's bits because like this 18 8 4 2 1. Yeah, so it clearly gives us 2 because that has the lowest amount of bits. So yeah, that is the solution. I think I explained it really badly, but it's really late at night. And yeah, I may do a redo of this. Why is there, am I tripping? Or is there 2? Whoa. Huh, well, anyways.